The direction of the force is perpendicular to that plane. If we take B as x-axis, as along x-axis, V as along z-axis, then V and B are forming the xz plane. Then the force will be along the y-axis, which is perpendicular to the xz plane or the horizontal plane. Next, there is another rule to determine the direction of force acting on a charged particle in a magnetic field B, and that is called the right hand palm rule. For that purpose, we will use our right hand and stretch the palm in such a way that the thumb is stretched, making an angle of 90 degree with the fingers. The thumb should make an angle of 90 degree with the fingers, so it is fully stretched at right angles, and then we will stretch it in such a way that it points in the direction of V, that is the direction of motion of the charged particles. The direction, the fingers are stretched in the direction of, let me first remove the arrows. Okay, so now the fingers are stretched in the direction of the magnetic field B. Thumb is stretched in the direction of motion of the charged particle. Now this forms a plane, and then F will be directed along the outward drawn normal to this palm, or in other words, it will be perpendicular to the plane containing V and B, and the plane which contains V and B in this case is our palm, the palm of our right hand. Let me repeat it once again. We place our palm in such a way, the palm of the right hand, in such a way that the stretched thumb indicates or points in the direction of the velocity of the charged particle. The fingers point in the direction of the magnetic field B. Then the outward drawn normal to the palm will give us the direction of the force acting on the charged particle moving with the velocity V in this direction and placed in a magnetic field directed in this direction. Now it's time to go back to the initial slide, and where I asked you a question that what would be the force acting on this charge Q in these three figures. Now I'm sure you will be able to answer the question. Here Q is at rest having V equal to 0, and here Q is having some velocity V parallel to the magnetic field, and here the same charge Q is having the same velocity V moving at right angles to the magnetic field. So your answer must be that the force is 0 over here because V is equal to 0. It is 0 over here as well because the angle between the B and V is 0, which makes F equal to 0, and here it will experience the maximum force, but in which direction? V cross B is directed out of the page. That is, the plane formed by B and V is the plane of this figure, and if you have to determine the direction of the force acting on this charge, the magnetic force acting on this charge, it will be out of this page, or it will be directed towards you. You can also determine the direction of the force using either the palm rule, right hand palm rule, or Fleming's left hand rule in this case. So you must verify whether it works or not. Now a question arises why a static charge does not experience any magnetic field. That is, the charge which is at rest does not experience any magnetic field, while a moving charge does experience a magnetic field. Now what is the answer for this question? The two charges interact with each other through their electric fields. If there is a charge q placed at certain point, it has a region around itself which is called the electric field. If another charge enters in that region, it will experience a force. But why it feels that force? Because there is an electric field around this charge as well, and the two charges are interacting with each other through their electric fields. That is, a charge q produces an electric field around itself, and then that electric field interacts with the other charge which also has an electric field E, and through that electric field it will interact with this charge q. So E is the factor with the help of which these two charges interact with each other. Now if there is a body which is neutral, on which this charge q is 0, then this interaction is not possible between q and that body. It feels only a charge. This electric field is the reason why they are interacting with each other. So a charge will feel only another charge, not a neutral body, because that neutral body will have no electric field. Just as your eyes cannot hear, they are designed to view something, or they are designed for vision. So they are not able to hear. Similarly, your ears are not able to see. Your ears can feel only sound, and your eyes are sensitive to light only, and they can view things only if light enters your eyes. So it is the sensitivity of one thing with respect to the other. So the charge has a sensitivity to another charge only. It has no sensitivity to the neutral bodies. So in the similar way, we can explain the effect of the magnetic field. So just as two static charges interact with each other through their electric field, two moving charges can interact with each other through their magnetic field. Now the static charge has no magnetic field around itself. Same is the case with this one. There is only electric field around them, so they will interact through their electric field, or they will experience only the electric force exerted by one on the other. But a moving charge is just like a current. So a current carries a magnetic field around itself. So the moving charge will produce a magnetic field around itself, and when another moving charge comes or enters that region around this charge, it can experience that magnetic field through the magnetic field created by this charge. So the magnetic fields of the two charges is responsible for the interaction between two moving charges. So one moving charge can experience the magnetic force exerted by the other, and similarly the first one will also experience a magnetic force exerted by the second one, and this is possible through the magnetic fields which they produce around themselves. Similarly, since it has a moving charge has a magnetic